Welcome back, students, to the fourth video on limits. So, as I promised on the couple of last videos, here's a set of rules of limits that we may consider to actually help us evaluate some of the limits we have seen so far and that we will continue seeing in the next couple of videos. So let's go over that quickly. The limit as x approaches a of a constant is a constant. So for example, the limit as x approaches 7 of 100 is 100 no matter what x approaches. Limit of, we recognize this, the equation of a line. So I can replace x with a and get ma plus b. Perhaps the most important one in the list, limit as x approaches a of p of x. That's p of a. So I can replace x by a again, provided that p of x is a polynomial. Remember polynomial from the review videos, like x to the n thingy? Well, that's the rule that applies here. Now this one, limit as x approaches a of a function plus or minus another function. I can split the limit and give it to each. Sometimes we refer to this as the limit of a sum is the sum of the limits. I could also say the limit of a difference is the difference of the limits as well. A similar rule applies for multiplication. The limit of a product is the product of the limits. So I can break the limits in two, and I can do the same for division. The limit of a quotient is the quotient of the limits. Finally, the limit of a function raised to a power is, I can bring the limit inside the bracket, so it's the limit of f of x as x approaches a, and the answer to the limit itself is raised to the power of n. And it should be noted that in this case, n should be a positive integer. Why are these rules important? Simply because they allow us to take shortcuts, and the shortcuts we have been actually taking, I have been calling cheat. Let me show you on an example how these rules can motivate what we've been doing and calling cheating. So as usual, I'm going to erase this and allow you to perhaps copy what you need to copy in your notes if you're taking notes in 3, 2, 1. All right, so just maybe one example to illustrate how this works. So example 1, let us evaluate the limit as x approaches 3 of x plus 2 over x minus 4. Right? So let's think about the rules we have just seen and think about which one would apply. This is an f over a g, so this is the limit of a quotient. So I'm going to say that this is the limit of the top over the limit of the bottom. So limit of x plus 2 and limit of x minus 4. Each one when x approaches 3. Now look at the top. This is actually the second rule, right? mx plus b. So that's basically 3, right? Or perhaps I can do something even better. I can use the fact that this is a sum and I can break it in two. So limit as x approaches 3 of x, right? So limit of f plus g is the limit of f plus the limit of g. So the sum one. And that's the limit as x approaches 3 of 2. That will allow me to actually focus on a couple, at least one other rule that actually matters. So I'll do the same thing for the denominator. I'll split the difference into two limits. Okay. Now, limit as x approaches 3 of x. That's really like rule number 2, right? mx plus b, though the b is 0 and the m is 1. So I can replace this by 3. And that's what I wanted to show you. This is the limit of a constant, right? So what's the limit of a constant? It's the constant itself. So 3 plus 2. Downstairs, same thing, 3 also. And the limit of a constant is this. So that is actually 5 over minus 1. So the answer is minus 5. Interesting, but obviously there's a much faster way of doing this, and that way is actually the cheat. So also we could do the limit as x approaches 3 of x plus 2 over x minus 4. And we can do what we have been calling since pretty much the beginning of this section. We can do a cheat, which is basically to replace x by 3 wherever x is. And of course, this is 5 over minus 1, and it's equal to minus 5. Why is it equal to minus 5? Because of these rules. I can do the cheat because these rules are actually accepted rules for limits. So I won't do all these things when I need to evaluate the limit if I can actually use that really, really good shortcut, which is now justified by the rules that we have stated. Good? Okay. So getting rid of this in 2, 1, 0. And what I want to talk about now is the topic of special limits. There are 3 special limits that I would like to consider with you guys today. The first one is the limit as x approaches 0 of sine x over x. If you replace x by 0, you're going to find that this is sine 0 over 0, and you're going to find that sine of 0 is 0. We can do this on our calculator. And that is what? What is 0 over 0? Of course, I cannot cancel 0 over 0. Of course, this is indeterminate by now. You know that. So I have to find a way to actually evaluate this. And using my rules is not going to help me, because limit of sine x on top and the limit of x downstairs still brings me back to 0 over 0, which is a problem. In the case of trig functions, if I have to evaluate limits of trig functions, it will be best to tackle this problem using the numerical approach. There are other ways, of course, but this is probably the most straightforward. So how does that go? It goes as usual. We make a little table. The target value is 0. We're going to smack this in the middle. And then we're going to choose the first whole number on the left and the first whole number on the right in order for us to get closer to 0. So maybe here this is minus 0.1 and this is minus 0.01. That's pretty close to 0. Same thing on the other side, 0.01 and 0.1. Now we need to set our calculator in radians. Calculator in radians, not in degrees. It doesn't work when we put it in degrees. Degrees is not a mean of calculation. So we put our calculators in radians and we put minus 1 into sine x over x. What we're going to get is 0.841. When we put minus 0.1 into here, you can verify this on your own calculator. You're going to get 0.998. This one is 0.999, and there's even another 9 after this. So it's not hard to actually extrapolate where this value is going. It is quite clear that the limit as x approaches 0 from the left of this function is actually equal to 1. As we move to the other side, we're going to find a beautiful symmetry here, in part because sine x is actually an odd function. We're going to get the exact same value. At 1, I'm going to get 0.841. Here, I'm going to get 0.998. And here, 0.999, and even another 9. So that when I look at that progression from 0.84 to 99.8 to 99.99, I will also conclude that this time as I am approaching from the right of this function, I get 1 as an answer. Of course, if I just take a look at the middle value, 0, I mean, there's no value there because it is 0 over 0, right? If I want, I can put 0 over 0 here, but that is not a value that I can put into my calculator. So when all is said and done here, we'll remember that if the left limit is equal to the right limit, then we are allowed to conclude that the simple limit with no direction is equal to the value. So that is how we would actually tackle something that has a sine or a cosine or a tangent in it. And that would be my first special limit using the numerical method. All right, moving on to the second one in a couple of seconds. So let's erase this. So the second one that I would like to present you with is something that actually has an absolute value in it. I'd like to investigate the limit as x approaches 0 of the absolute value of x over x. So for this one, this is a special one because the absolute value sometimes is creating quite a few problems for the students. So how could we actually do this? Of course, we could do the numerical method, clearly, right? It'd be quite long. Let's see if we can perhaps be more clever about this than using the numerical method. Recall something we saw in the review videos, the definition of the absolute value of x. What is that equal to? Do you remember? It's equal to x if x is greater than 0, and it's equal to minus x if x is less than 0. So if we remember this, we can actually replace the absolute value of x by one of these two things depending on what the value of x is. And of course, this presupposes that we can investigate this limit from both sides. So let's investigate this limit from the left, and let's investigate this limit from the right. Okay, so here, if I am approaching 0 from the left, I am clearly less than 0. And if I'm approaching 0 from the right, you see, you broke down the two possibilities, and that will mean that I can replace the absolute value by the two different things depending on the case we're in. For example, here, this is the limit as x approaches 0. I don't have to write the negative anymore because I'm going to replace the absolute value of x. I'm going to replace this guy by what? I'm going to replace the absolute value of x by minus x because my x is less than 0. The x's cancel. This is the limit as x approaches 0 of minus 1. So it's minus 1. On the right side here, what do I have? I have the limit as x approaches 0. Now, actually, I don't need this anymore because I know that x is greater than 0. If I'm greater than 0, I can replace the absolute value by just x. Once again, the x's cancel. I get the only thing left is 1, and the limit of a constant is a constant. You will notice that these two guys are not equal to each other, right? Minus 1 on the left is not equal to 1 on the right. Alors, what does that mean? What is my conclusion? The conclusion is that limit as x approaches 0 of the absolute value of x over x does not exist. If we had tackled the numerical method, we would have come up with the same conclusion. On the left, I would have gotten a bunch of negative 1s, and on the right, I would have gotten a bunch of 1s, and I would have seen that the left and the right do not coincide. So a quick remark a quick remark. If you take a look at this from, if you take a look at this from the perspective of a graph of the function absolute value of x over x, if you sketch this graph, you would actually get something like this. So x and y. Now, to sketch this graph, you basically only have to make like a table of value, put in a lot of numbers, and this is what you would have. This is 1, and this is minus 1. And basically, one can tell that approaching from the right side, the y values are constant and always equal to 1. And approaching from the left, well, the y values are always constant and equal to negative 1. So basically, that just reinforces the findings that we have over here, saying that the left and the right are very different, and that the limit in the end does not exist. So that's just a little remark to reinforce, if you want, what we have done algebraically over there. Good. Okay, getting rid of this whiteboard in 2, 1, 0. Yupa. Okay, so one more special, very, very special limit to take a look at. And it is the third one. Now this one may be one of the most important one in the entire chapter. Limit as x approaches 0 of 1 over x. We would have been happy in high school to actually just consider the answer to this, meaning d and e, or undefined. That 1 over 0 in high school, we call it undefined, we call it does not exist, and that's perfectly good, right? Notice that this is not undetermined. This is not 0 over 0. This is not undetermined. So basically, I have that, and my purpose with this question is to see if we can dig a little deeper into the meaning of undefined. What actually does it mean? And for that, allow me to actually sketch the graph of the function 1 over x. It's again something we saw in the review videos. It's a graph that actually has asymptotes. The good old rational function that we spent quite a bit of time in high school with, didn't we? So it goes like this, goes like that. Now, here's the lowdown. Okay, if I want to know what happens when I approach 0 on a graph like this, I would be well advised to take a look on the left and take a look on the right and see what I get. Now, remember, like graphically, the approach is simply that we take some points. Let's start from the right. So say I am here on the x-axis. Maybe x is equal to 1 or something. And then I actually find what is the y value corresponding to that point. And the y value is about here. Now I need to get closer to my target. What is my target? My target is 0. So let me get closer. Let's say I'm here. That's pretty close to 0. Where's the function? Function is here, and the y value is there. If I get even closer, starting to be pretty close to the axis, maybe the point is over there, right? What value am I getting close to? These points seem to get closer and closer to what value? Because the curve actually goes up and the y-axis is an asymptote, it'll never touch, but it will keep on going up and up and up, and these points will keep on going up and up and up again. We say that this limit is actually equal to plus infinity. So a very special limit that actually has a non-real number answer. Let's take a look on the left. I'm here on the left of 0. Where's the graph? It's right there. What's the y value? It's about here. Let me get closer. Where's the graph? Here. What's the y value? It's about here. Let me get closer. So maybe here. As I get closer and closer to 0, those y values, because the y-axis is an asymptote, you're going down and down and down. They will never stop because it's an asymptote and the graph never connects. That's minus infinity. Now, why this? Why am I showing you this? Because here, basically, if I did a cheat, I would actually get 1 over 0 plus, and that would be infinity. And here, if I did a cheat, I would actually get 1 over 0 minus, and I get minus infinity. All this to say that we are getting something a little more precise here than d and e, or undefined. 1 over 0 is still d and e, it's still undefined, but in the context of this limit in particular, we know that the answer can be refined to the point of saying it's positive infinity if you're approaching from the right, and it's negative infinity if you're approaching from the left. So the bottom line is that the limit as x approaches 0 of 1 over x can be said not to exist, can be said to be undefined, and can also be said to be, again, depending on which part you approach, plus or minus infinity. So this high school notion of 1 over 0, which we called undefined or d and e, in calculus takes on another dimension, the dimension of plus or minus infinity. And there we are entering slowly the realm of calculus, because really, ladies and gents, calculus is how do we deal with infinitely large and infinitely small numbers. That could be one way to actually perceive what calculus actually is. How do we deal with the infinitely large and the infinitely small? So, with these 3 special limits, we will put an end to this video, and we will continue our learning of limits the next time we meet. So take care and see you soon.